All right, welcome back. I'm Corbett. I'm going to be your translator for this session from the CIE, which is Chemistry of Indoor Environments Grand Conference. This is what we learned after 10 years of research from some of the world's top researchers in the field of chemistry who have now moved indoors. Thank goodness. By the way, I've been missing a couple Mondays, and that is because I am not being paid to do this. So Grace and I just do this translation work because it's our hobby. We like this kind of thing. So this is going up on our channel as just like a fun thing. We hope that this helps you. It's certainly making me smarter about doing home performance and building science. And I hope that it's working for you as well. What we're talking about today with Vicky Grassian is a high level treatment of surface chemistry and what they have been learning about this. Vicky is one of the pioneers of surface chemistry research. So let's get into it.
Okay, so it's great to be given the first talk on this, what I think, important session having to do with surface chemistry and indoor environments. And I co-organized this with Rachel. So thank you, Rachel, for all you've done and for the introduction. So let's just start by looking at that National Academy report, Indoor Chemistry Matters. And what I did is I did a word count to make the point that indoor surfaces matter. Surfaces play a role in indoor chemistry and indoor air quality, acting as a sink, acting as a source, and also being able to transform chemicals from one type into another. And we haven't talked about that too much here, and I'll mention some of that work.
One of the reasons that she is bringing this up at the very top is that she wants to make the point that surfaces are more important than gases based on how these chemists who have founded this research have talked about this, and she's kind of in the minority. So the way that a lot of these chemists, and you've seen Rich Corsi on our channel, I'm linking a hugely long video with him. You've seen Charlie Weschler and Bill Nazaroff, which she both mentioned just now as well. They were one of the first sessions in this series, and I'm linking that on screen right now. And all kinds of different people who have been both on this channel in general and also on our show, Home Diagnosis, which is on PBS. And please do go check that out if you haven't seen it already. All of them are measuring what is going on in surfaces in the air. So she's going to talk about this some, but she's one of the only people who's really all about like, hey, if we want to know what's going on surfaces, we got to measure the surface, not try to kick things back up into the air where we can grab them. That's the technique that's used by a lot of these atmospheric chemists who are the people who are in this room that she's presenting to right now. They're atmospheric chemists, so they work in gas phase. That's what their favorite thing is. All their tools are gas phase tools. So in order to measure what's going on the surface, they have to then do things to the air to kick things up from the surface into the air where they can then grab them and measure them. And that's one of the things that she's making a big deal about. So it might be, I just want to make sure that that was clear up front because it seems like it was a little subtle.
So Charlie already showed this slide. This is surface chemistry, the reactions and drivers. This is a report that we wrote and we published in the journal Chem, which is, a high-profile chemistry journal. And we did that on purpose because we want more chemists thinking about these problems, okay? So we publish a lot in ES&T. We heard about that, or environmental science processes and impacts. One of the things that I have wanted to do is publish in other chemistry type journals, high profile chemistry journals, bringing more people into this important field with their tools and their ideas as well. And that's what the Sloan program really started. And I'm trying to get that to even increase further as somebody who is in that program.
Okay. Quickly about this slide, Vicky is one of these people who puts a lot of information on each slide. So up on the top left here, you can see surface reactions involving oxidation. Oxidation is reduction. Oxidation is fire. That's when I say the air is literally on fire. It's not a figure of speech. It's literally happening. It's literally the same thing as a campfire or as a rocket taking off or lightning. Certain molecules are giving to other molecules. Nitrogen oxides are generally always bad. These are things that are created by combustion. Organics, we know what those are. That's anything that has carbon on it. And by the way, those things, organics, VOCs, volatile organic compounds, have carbons on them, and those are tinder for oxidation. So oxidation loves to happen on these organic molecules. Halogens are anything that have chlorine in them. So it's chlorine-based anything. And like halogen bulbs that you might have in your home, I have some in my home. Those are good in the right setting. But if the halogens are not inside of a light bulb used for making light, then they can be bad, just like anything, right? Asbestos is a great material when it's inside of a glove that you're using to hold molten glass or something like, you know what I mean? Like, but if it's in your lungs, terrible. So right place for the right time. Acids and bases. She's saying this instead of pH. She's pointing out that acids and bases, the acidity or the basicity of a home has never been tested before CASA, which is part of this CIE research program. And so nobody really knew what it was. We call it pH. pH is actually not exactly the right way to say it, but it's acidity or basicity of a home. And then materials. So down here, these are in order of complexity. So you've got gypsum. When we talk about drywall, the structure of how the gypsum is inside of the sheetrock that's on the wall is essentially the same with a few additives as how it is in the ground. So it's just like that. Concrete is like basically just minerals that come from the ground. Wood is wood. It's exactly how it is. Carpet being at this point completely synthetic. It's plastic. It's a very complex shape. It's made of multiple different chemicals that are all kind of woven and bonded together and things like that. So, and also surface area wise, this is the most complex. So we need a mechanistic understanding of how these things might affect these surfaces. And then we also need to come in with this reactivity, which is what chemistry is. So it's chemistry is the formation of new chemicals that were not there to begin with. We have a couple different things that can drive this. Light being one of them, sunlight specifically. Like artificial light does work also, and there is a fair amount of chemistry happening right around a light bulb, but as you move away from it, it precipitously decreases. Surface acidity, which is why, again, we need to study the acidity and basicity of homes. Temperature, and also humidity, I'm sure can affect that. And then coatings, meaning paint. And she's going to get into this at some point. So, and then you can see that on the surface here, we've got water and organics kind of mixing together. And this is where heterogeneity, what we talked about in the last session with Tara Kahan, comes in, because it's like, it's different depending on where you are, is basically what heterogeneity means.
We wrote about different types of reactions, surfaces that could be studied, some of the drivers, and even some of the complexity. And this paper came out of a workshop that was sponsored by the Sloan Foundation. And we did this at the University of Michigan in 2018. Andy Alt and I were co-chairs at that time. Okay, so I'll tell you a little bit about some of the things that we did specifically. That was just some overview, and we're going to hear from other speakers during this session. I put pictures of the people who were most recently in my group. Sorry, Mike, you were in the video, though. That was good. Okay, Leora also in the video, but she didn't work on this in my group. She did that in Nina's group. So we're interested in a few different things in our most recent grant. We were interested in nitrous acid, HONO formation from surface processes. I'll give you some insights into some of the things we learned from that. Organic thin film formation, and also just how different organics interact with surfaces on a really molecular level. Okay, so we're very fundamental in our approach, but always trying to look at the bigger picture as well. And also we have interest in cleaning products, surface chemistry, as well as emerging contaminants. And Carla and Cholafan are here, and they were able to give posters last night. So, and they told me they got a chance to talk to many of you, so that was great.
Okay, so nitrous acid formation from surface processes. Nitrous acid, HONO, is what they call it, and it's HO2N or whatever you want to. They spell it differently. They like to say HONO. It's fun to say, so let's say it. So HONO, nitrous acid, is an interesting molecule because it drives a lot of NOx chemistry, nitrogen oxides, NO, NO2, and in some cases then NO3 forms. Outdoors, NO3 is only around at night because the sun breaks it apart in the daytime. Indoors, we can find NO3 during the daytime because the sun doesn't shine inside. So that's one of the things about moving indoors, again, that like it's different inside than outside. And so HONO can also dissociate and form OH and NO. And NO is bad for us. It's nitrogen oxide. And OH is hydroxyl radical, which is a super reactive. It's more reactive than ozone is even. And we generally don't like ozone inside of homes. So you can see where that is. This, first of all, cleaning products over here. I asked her, do all cleaning products create chemistry? Chemistry being the formation of new chemicals that were not there to begin with. And she said, basically, yes. Either they are reactive themselves, like, for example, hydrogen peroxide can oxidize things. Chlorine, right, like bleach-based stuff, oxidizes specifically. It causes reactions. Or if you're using like lime or lemon-based cleaner, like pine sol or something like that, those are all terpenes. And that isn't a reactive species, but what that is made up of a bunch of things that are like tinder for reactive species. So when the sun shines in through the window and it finds what's left over from your pine scent or your lemon scent or whatever it is, that is going to then create chemistry. And so it's either the reactive species, the spark, or the tinder for this. And then the last thing over here is organic thin film formation. This is basically covering everything. We've gone over this on the show and on this channel before. But what she said is actually this heterogeneous thing, which is it's different. It's not a monoculture everywhere. It's not homogeneous. It's the same everywhere. What we really have is this patchy kind of thing. You'll see some images of this, but on surfaces, we like to say that everything is coated with a thin film of grease or oil. But it's not just a thin film. It's actually kind of patchy and splotchy, and it's based on oxidized organic chemicals. That's the thing that makes it stickier. And so then things tend to clump, just like clouds grow out of a seed. That's kind of what's happening on surfaces as well.
So HONO formation from different indoor surfaces. I think this is a great paper. Okay, pass it around because I don't think people have picked up on it quite yet. But we asked a very simple science question. How does material surface composition play a role in indoor gas phase HONO concentrations? And we looked at 4 different samples, a cement sample, a painted wall. We heard about the importance of painted walls, a clay surface, kaolinite, as well as a zeolite, which is a porous material. And these materials are used in building construction. And we wanted to measure NO2 and HONO, looking at the NO2 hydrolysis reaction, which I'll show you in a minute, plus nitrate photochemistry.
Quickly, cement or concrete, cement's an ingredient in concrete, you can find raw in homes, right? The floor of my crawl space is concrete, which has cement in it. Painted walls, we have those in homes. Zeolite and kaolinite, those are both ingredients that you can find, like she's saying that they're partial substitutes for cement in lightweight concrete. That sounds like it would be plaster. So just FYI, this is where some of the kind of plaster and clay-based and porcelain clay and things like that we were talking about, perlite, that Rich Corsi was talking about in his video, which again, I linked at the beginning of the session. They were saying that those can capture ozone, like sequester it and just lock it away forever. Those are the kinds of things that I think these minerals are getting at.
And we were measuring in the gas phase these molecules, NO2 and HONO, using an incoherent broadband cavity enhanced absorption spectrometer. And Carla had that on her paper, on her poster last night, and she's looking at the role of organics. And it's a little complicated, but it's an interesting question that she is looking at.
Incoherent broadband cavity enhanced absorption spectrometer. I'm a tool guy, like I love testing. So I just wanted to tell you that the reason she's talking about this instrument is because no one makes this instrument. They made that. It has been described by different people, but it's not like something that anybody manufactures in the world. So they made this thing. Incoherent means it is not a laser. I don't really know anything aside from that, but that was like something that I thought was very interesting.
Okay. So we looked at, on those 4 different building materials, NO2 hydrolysis, and that's shown reaction 1, and nitrate photochemistry, because you get nitrate from that NO2 hydrolysis reaction. And we wanted to ask the question, do we see HONO forming from these different surfaces? And so let's just go right to the answer I put on the side: HONO, HONO, no HONO, no HONO. So these different surface materials, because oftentimes people say it doesn't matter what the surface material is because it's an organic coating. Well, here we show that the surface material matters. So this is my pushback on that comment, all right? And so we really see that it does matter. And what's happening is that the amount of HONO produced is related to whether nitrite stays on the surface or forms HONO in the gas phase. So how do we know that? We took these surfaces and we extracted from them whether there was nitrite, also nitrate. I'm just showing the nitrite here. And we see that for surfaces that did not produce HONO, there's a lot of stored nitrite. Now, mind you, this might be a reservoir that later, if under different conditions of acidity in the environment, could become HONO in the gas phase. But here we're seeing HONO forming on some surfaces due to the hydrolysis of NO2 or the nitrate photochemistry, and other surfaces not. You can say that should drive our thoughts about how we use these building materials. Maybe you can say that because these store, but this storage might become something in the future. So I thought that was an interesting example, and Pandit wrote that paper that we published in 2022 showing the different surfaces produce different HONO and why.
Okay, so just to back up here, if we have painted walls or kaolinite, then we are going to be creating this HONO, this nitrous acid, which then is going to fuel NO, nitrogen oxide chemistry, which again is generally all bad. She's focusing on NO a lot in this session because NO likes to be in the air more. NO2 and NO3 would be bad in air, but they stick to the surfaces generally. And if they were created on a surface, then they just don't tend to make it up into the air at all. So just unlike combustion, combustion is actually creating it in the air, and then it has to find a surface to stick to, and then it can break down from there into NO. That would be bad. But anyway, this I think is interesting. I don't have any particular, like, she's not saying painted walls are bad here, I don't think. And that would be, I think, a pretty weird and inflammatory thing to say in the world, because we have painted, not just painted walls, but painted furniture, painted nails, painted like equipment. We've got, I mean, everything has paint on it. So anyway, that's just like just a little thought there. Don't take this and be like, oh, I can't have any paint in my house and I can't have any walls in my house. I need to have everything be cement, because that has downsides too. If you looked at the earthquake episode from season 3 of Home Diagnosis, earthquakes do bad things to concrete buildings. You want it to move a little bit too. And by the way, nitrite is the same thing that we're avoiding in bacon or in like processed meats. You don't want to have nitrates and nitrites in those. And so this is the same exact chemical.
The other thing we were interested in this program was looking at the interaction of organic compounds with indoor relevant surfaces. We took a different approach than what you've heard so far, where people were measuring gas phase. We looked at the surface interactions with silicon dioxide and TiO2. You can think of this as a model surface for glass or self-cleaning surfaces, or you can think about this as a fairly unreactive surface compared to a reactive surface. However,
okay. Before she has a lot to say, and this slide made me, I feel a little bit nauseous even looking at it right now. She's making a lot. This is like bibliography. Okay, so don't get freaked out. I want to explain it. What she's saying here is we've got up here terpineol and linalool. Both of these are byproducts from terpenes, which we talked about in cleaning just a few minutes ago. So that's things like pine sol or citrus-based or lemon scent cleaners. oh, and this is limonene. This one, 6-MHO, is 6-methyl-5-heptan-2-1. That's my favorite molecule right now. That is the main secondary byproduct of oxidation reactions with squalene in your skin oil. What they're testing here, SiO2 and TiO2, glass powder, SiO2 silicon dioxide, and TiO2 is titanium dioxide, the white in paint historically. That's how they get paint to be so white. Also, they're using it now. They've kind of discovered that it has this weird chemical thing where it's a catalyst for chemical reactions. So it's used in what's called self-cleaning surfaces. The jury is still out on how exactly that works, because there's two sides to every equation. If you tear something apart over here, okay, you did that, but what did you make? What is now, in the world because you tore it apart? This right here, dihydromercenol. So that's a body spray. It's not from Axe specifically, but like you're familiar with teenagers spraying themselves with stuff. So that's where that comes from. These papers down here that she's mentioning, by the way, this is from Home Chem, this is from Home Chem, this is from Home Chem, and then this is from CASA.
However you want to think about it. And what we were able to do is really work with the modeling consortium by integrating our laboratory measurements of spectroscopy of surfaces with MD simulations and kinetic modeling. And we did this for a number of compounds. We have many papers. I didn't count them, 10, 15, just a number of papers that we were able to write. And I just list a couple of them here. The other thing we wanted to do was we wanted to look at surfaces placed indoors in CASA and in Home Chem, and then bring those back and use, microspectroscopic probes to better understand the heterogeneity of surfaces in indoor environments. And we have some papers published, and we worked with Rich Corsi, Delphine, Nina, and you heard from them in that video. So, surfaces are sinks and sources of organic compounds. Here's an example, limonene on silica, SiO2. And so here in the middle is the experimental data. One is we expose these surfaces to limonene. We use spectroscopy to follow that these limonene is taken up by the surface, so it's surface absorbed. Then we see that the surface is saturated with limonene. Then we remove it, and so it desorbs. So now it starts to be a source of limonene as it leaves the surface. So this is just trying to get your mind about how we think about things. We could model the absorption and desorption with Manabu and his kinetic model. And we worked with Doug Tobias to look at how these molecules, in particular limonene, was interacting with these surfaces. And in fact, chemical sciences picked this as, science of the week, and they put together this little picture of, what's sticking on my glass. So that was kind of nice.
So these graphs that she's going to be showing at this point are all actual surface measurements, not assumptions about what's going on the surface from gas phase measurements. Like we were talking about, she's like a real, let's measure the surface kind of a person. Let me show you this graphic that they created. So this over on the right, the glass here, this is that heterogeneity thing that we were talking about, where like there's stickiness in more or less. So it's like there's a topography to these surfaces. And one of the things that we'll hear soon from Jinan Lee is that actually cleaning glass, which turns out to be kind of important if you want to limit things. We heard from Barb Turpin in one of the earlier episodes about how clean glass has almost no chemistry going on it, and it doesn't tend to grab things. Soiled glass, authentically soiled glass, which is the kind that we have in our homes, tends to grab a lot of stuff out of the air and then can do chemistry with water films that are on those. And so you're seeing here that the molecules are going to get grabbed by these little piles of just gunk that you can't see, but it's there. And so understanding that this is happening on every single surface in our home, including our clothes, including our skin, is, I think, an important part of all of this conversation. Because if you're just taking this information and being like, oh, interesting, it's happening, but I'm not thinking specifically, like I'm looking at my books over there, which I haven't wiped down, there's definitely stuff stuck to those, and then it's coming back off, it's doing chemistry and coming back off as new things, and all of this then I find really interesting. So I like thinking about this kind of stuff, and I hope that it doesn't worry everyone else. But like this is really what we're trying to talk about here is like, especially kids, when we are breathing this stuff and it's in the air, and we're actually going to talk about dermal exposure in a few minutes here, getting things into us through our skin. All of that becomes important because the health side, I think we can all agree, health in this country and in the world in general is kind of screwed up. Like we've got a lot of things going on that are supposedly brand new. Mental disorders, we've got physical disorders, we've got behavioral and endocrine disorders and all this stuff that's like something is wrong. And this seems to me to be like a pretty easy connection to make.
Then we went to, so that's limonene, we went to oxygenated organic compounds. And what I'm showing you on the left is that we see limonene in blue really comes off the surface very fast. When we look at other compounds, oxidation products of limonene or oxygenated compounds, you see they slowly come off. So again, this is your first initially a sink and then a source. And so that correlates very well with what we know about organic thin films, where we have done microscopy and spectroscopy on these films, and they're mainly organic compounds that are sticking to the surface. And Rachel O'Brien wrote a really nice paper that we contributed to there.
Okay, so this is about VOCs, how we categorize VOCs. Volatile means it likes to jump off the surface and be in the air. There are a whole bunch of gradations of this, and Jinan Lee, who's in a couple of sessions, gets into this way more in depth. He was telling me that there is SVOCs, which are semi-volatile organic compounds. There's, I believe, intermediate VOCs. There's extra heavy VOCs. There's all kinds of different like kind of classes of them. So some of them really like to stick to surfaces. Some of them stick to surfaces, but they're happy to also be in the air and they'll come and go. Limonene clearly is one of these that just jumps right off the surface and gets into the air. And this is when you're cleaning and you smell that lemon scent or that citrus scent. That's what's happening is you're putting it on there and then it's like bam, it's bouncing right up into the air where it can then be doing photochemistry and interacting with other things and getting into us. This stuff where it's sticking on the surface, it just gives it more residence time. Residence time is what they're talking about when they're talking about how long something has the opportunity to interact with other chemicals and maybe do chemistry. And essentially, we've talked about this idea of a battery or a sponge for all surfaces in the home. And they all end up doing this thing where we're charging these surfaces with a bunch of different molecules. And then they get to sit there. And then when the air doesn't have enough of those molecules again, things move from high concentration to low concentration. So then it'll jump off of the surface and into the air, and then it kind of recharges the air with that. And the same thing happens with humidity. That's, hygric buffering is what you can call it. But anyway, this is always happening. And that's why the surface to volume ratio in a home becomes so important because we've got so many surfaces in here. Even if you're living in like a, Scandinavian design kind of environment that has very little tchotchkes around and doodads, this stuff does really start to matter.
I'm just going to go real quick on a few other things. So the surface chemistry of other oxidation products. Has anyone looked at 6-MHO and its surface chemistry here? I did. Okay. And has anybody looked at 6-MHO surface chemistry anywhere? The answer is no. There's not one paper. So these contaminants, nobody's studied their surface chemistry in any form. So I'm a surface chemist by training, and so this is really exciting for me. So we looked at it on silica. We saw it being taken up, steady state, slow desorption. I just put 6-MHO relative to some of the other compounds, so slower than limonene and faster than some of these others. But when we look at this compound on TiO2, a different surface, a reactive surface, we form new compounds. And when we can see that in the FTIR spectra, as we monitor the reaction, we can then extract and look at what these products are, and we see oxidation and dimerization products. So the chemistry is really interesting. Here's my last slide showing bleach plus terpenes. So we followed this paper that was your group, John, right? Wang et al. I thought that was really interesting, where you form chlorinated products. Well, guess what? Those chlorinated products more strongly adsorb to surfaces. And so Cholafan, who's here, looked at that, and similar to the oxygenated products, they stick more strongly. And can you initiate further reactions? And yes, the answer is yes. We have that paper under review and it should be out there now. We use in part this Teflon chamber that Mike built when he was there to do those studies.
Okay. That was a lot to go through. And like the one thing that I'd like to have you be taken away from all of what she just said is chemistry and oxidizing compounds and all that stuff. We just don't want to be doing that. So this is my plug, as I do every one of these generally, to not buy any air cleaning device that is more than just a fan and a filter. Your home is already a chemical reactor, just with the sun shining in through the window, just with you turning on lights, just with you breathing out we breathe out ammonia, we're breathing out formaldehyde. We've got all kinds of VOCs coming out of our body that is tinder for these oxidation reactions. We live in places where other people live. Therefore, there's going to be pollution like smog coming out of tailpipes. Ozone is a main ingredient in that. It's coming in through the window or through the cracks in your house, and it's then doing chemistry. You're using bleach. You're using cleaning products that are going to be creating oxidation. You do not need an extra chemical reactor inside your home that's fueling more chemistry. So please don't buy something that goes inside your ductwork and is a blue light or an ionization or an ozone generator or hydroxyl radical generator or anything like that. Please don't let your family and your friends do that. These companies want to sell you crazy stuff that they don't understand, and they don't understand it because if these people don't understand it, the manufacturers of those companies definitely do not understand it. And the salespeople are very convincing. So your HVAC guy, if you're an HVAC guy, please stop doing that. If you are hiring an HVAC person and they offer to install blue lights in every one of your HVAC systems, which you might have multiples of, please don't let them do that. Okay, so less chemistry is good because we don't understand what's happening already.
So in situ surface measurements provide insights not obtained from gas phase measurements alone. I will die on this hill.
Okay, she's serious about this, and I want to just tell you why. So I took some notes on what exactly the deal is, because like I told you before, she's one of the few people who's like, we need to measure the surfaces, not the air just above the surfaces, and trying to get things to happen. So in the field of heterogeneous catalysis, which is what kind of she's dealing with, we're looking at how to make chemical compounds. That was what she was trained in. And so she was telling me about the history, and the gas phase was studied from the 60s on. And in fact, atmospheric chemistry in the kind of climate crisis of the 70s, and when people started caring about the ozone layer and things like that, it was all about atmospheric chemistry, meaning what's happening in the air. And in fact, what she was pointing out to me is the ozone layer hole has to do with surfaces. So studying surfaces is critically important, and that's what she's making a big deal about. COVID showed, when we're talking about COVID, which we did in the last session, it's not about surfaces, right? When we were so freaked out about like your package being delivered to the front stoop and then you like disinfecting it or waiting 24 hours to touch it, surfaces are a lot less important for that pandemic. The aerosols, the stuff in the air, was way more important. So standing 6 feet away from people was like, it's so surface level. So really the air is also very important, but the testing is what it's all about. And so she's saying, like, if surfaces are important for some of this stuff, talking about everyday life from now on, which hopefully we don't have to deal with that pandemic again, surfaces are very important, and surfaces play a huge role in air quality, which is what she was saying at the very beginning of the session. And so we gotta test the surfaces.
Emerging contaminants indoors and their interactions and transformations with surfaces, sometimes there's just nothing known about their surface chemistry. It's rich, and we need to understand it better, okay? Cleaning surfaces can be important in indoor air quality, not maybe for COVID, but as Lee et al., we'll hear about that today, and Delphine, was shown by surface and gas phase measurements. So we made in situ surface measurements in CASA for the first time and used some techniques for the first time. Outdoor indoor air exchange, we heard about that, especially in a changing climate, is key to understanding indoor air chemistry. And we do have a roadmap for future efforts on the role of surfaces and just on indoor chemistry. And this clarity, it's clear what our roadmap is a legacy of you, Paula, and your advisors, the Sloan Foundation, and that NAS report that a lot of us worked on over the last, for about a year and a half. And so with that, I'm looking forward to hearing the other talks.